Hey y'all, next up we're going to talk about IPv4, and this is really probably where we're going to spend the most time in this section on network layer protocols because, as I said earlier, IPv4 is really the workhorse of the network protocol stack. It's most likely the most prevalent network protocol in the world, and it's what really allows us to identify devices at the network level and facilitate communication between devices on different networks. So there's a lot of protocols that we need to make the internet and global communication work, but this is probably the most important and most critical to that. So we're going to spend a little time picking it apart and talking about some different aspects of it. So the IPv4, as I said, it's the most common network layer protocol, and it's defined in RFC 791. I try where I can to list the RFC numbers here because this course is all about practical packet analysis. And what that means is we're not going to go through every single field in every single protocol. I don't think that's practical. We're going to go through the fields that I think you're going to encounter the most often and the ones I think you're going to need to have the best understanding of in relation to normal and abnormal stimulus and response, namely the things that can help you. So I put the RFC numbers in here so you can go back and reference things that maybe we don't cover. And of course, I'll provide some other resources as well that are a little bit more user-friendly than going through an RFC document, which I'll tell you is not the most exciting thing in the world. Now, the IPv4 protocol contains a lot of useful information. We're going to go through all this and show some examples. But of course, first and foremost are source and destination addressing. So we're talking about network or IP addresses in this case. It contains information that is needed to get packets from one place to another. Of course, that includes the addressing information we just mentioned. Includes the information that will allow us to route packets across the internet. Important there because if without that, we would only be able to communicate within a single network, and that's not going to get us where we need to be. It also contains the transport layer protocol information. We have an IP packet and it's encapsulated other data within it, and that will include the transport layer protocol data is encapsulated there as well. So this is typically going to be TCP or UDP or something along those lines. And finally, it's going to contain packet fragmentation information. So if a packet is too large to traverse a network of a certain size MTU, and we'll talk about MTUs later, then the IP header will contain the fragmentation information that will allow that packet to be broken up into chunks and then reassembled back on the other end. So clearly, a lot of important things contained in the IPv4 packet. So let's go ahead and start diving into the structure and nature of those different components. Behold the IPv4 header. It's a very important header, and while it may not look entirely glamorous, it does a lot of important stuff for us. So we're going to dig into that now. We're going to go through some of the fields that I think it's important for you to know as you're analyzing packets along the way. We'll start right at the beginning, and we'll talk about the version field. And we see that it is in the higher order nibble of the 0 bytes, so that very first byte there in the header on the top left. And it's a pretty simple field. It's really just going to have two values for your purposes here. Generally, it's going to be IP protocol version 4 or 6. Of course, we're talking about IPv4 right now, so generally that should have a 4 in it. When we talk about IPv6 later, it would have a 6 in it, so really straightforward. And the lower order nibble of that first byte or byte 0 is the header length field. And this is going to tell us the total size of the IP header. And that's important because the IP header can vary a little bit in size. By default, it's generally going to be 20 bytes, and that's what you're going to see in most cases. But there are some options, and you see that down there in the second row from the bottom. There are options that can be included, and depending on what those options are, that header length should be specified as such to let the system know that's interpreting the packet what the length is, so it knows where to stop processing that and where to start looking for the next protocol header that's identified in the protocol field. So as I said, the normal size of an IP header is 20 bytes, which also happens to be the minimum size, pretty small here. Now it's important to note that this is a calculated field. So when you see a 20 byte IP header, the value in this field is actually going to be 5 because whatever is in this field is multiplied by 4. So in this case, you would see a 5 in there, you'd multiply that by 4, and you would get 20 bytes. So just remember that that is a calculated field, and we'll encounter a few of those throughout the course of our journey here. Calculated fields where you have a specific value and you multiply it by something, and that's really done to save space. You don't need as much size in the packet header if you have a multiplied field like that. You just have to make sure it's acceptable that all of your resultant values are okay being multiples of whatever you are multiplying by. Now, an important note here, a pro tip, is that generally you can identify the start of an IP packet header by looking for hex bytes 4500. So that's going to be IP version 4, header length 5, and type of service, which is the next byte 00. We're not going to talk about the type of service field. It's not too important for our uses, but most of the time you see that it's going to be 00. So if you're looking at a hex dump and you're trying to pull it apart, one of the tricks I use and a lot of people use is to just look for 4500, or at least just 45. And if you can spot that, then you can probably spot the beginning of a new IP header. And if you're looking at a bunch of packets that are jammed together, you can probably use that as a basis for dividing the packets up. If there's an Ethernet header in there, you have to take that into consideration, but at least gives you a place to look where you can start counting in either direction. 4500 is pretty easy to spot even when you're looking at a lot of data. So that's a tip that I've grown to use quite a bit as I've advanced a little bit more in my packet analysis abilities. The next field that's of interest to us is the total length field, which starts in byte 2 offset from 0 and is 2 bytes long. So you see that there in the first row on the right. It's total length, and that tells us the size in bytes of the entire packet, excluding the data link layer. So remember, I mentioned earlier, the data link layer is often not discussed in relation to the entire packet when we're doing some of these calculations. So in this case, we're talking about the entire packet size minus the data link layer. And that's useful information for a couple of reasons. One of the reasons is oftentimes the transport header that is included doesn't include the data payload size. So you don't actually know the size of the data payload. You can figure out the size of the different headers, but you don't know the payload size. So you have to do a little math to get that. And of course, systems are programmed to where they can do this math as necessary. And you can do it pretty easily as well with a simple formula. And that's pretty straightforward. You take this total length field, which is going to be the entire packet size, and you subtract the IP header length and the transport protocol header length, whether it's TCP or UDP, and the remaining value are your data bytes. So that's how you determine what your application layer protocol size is when you don't have anything else that's telling you that. So IP is useful and it gives us a couple different length values that we can use to determine that sort of thing. So for example, if you had an IP length value of 492, an IP header of 20, and a transport protocol header of 28, so it's a TCP packet, you could subtract, you take 492, subtract 20, subtract 28, and you're left with 444, which is telling you have 444 data bytes or application layer and data bytes that are available in that packet. So that's a trick to figuring the exact packet size out. Now these aren't real numbers. I just use these for a simple example, but you kind of see what we're going with here. So the key difference here is to make sure you know what the difference between the header length is and the total length. Header length is the length of the IPv4 header exclusively, just that header. Total length is the length of the entire packet, and that's useful for figuring out what the data byte size is if you subtract all of the other protocol header lengths.